Welcome to solverfy.
This is the answer to Chapter 15, problem number 53 from the Smith Organic Chemistry textbook. And this problem asks us to draw all stereoisomers of molecular formula C7H15Cl when 3S3-methylhexane, which I've drawn here, is treated with chlorine. And then we're asked two other things about trying to separate some of these products. Okay, so to get started, we need to draw all of the isomers here. So the first one is going to be just the product when chlorine adds to the terminal carbon. So like this. So there's one product. So next, the chlorine could add to the next carbon, which would give it, so it can add from one of two directions, right? So it can add like this, so it'll be cis to the methyl group, or it can add so that it is trans to the methyl group. So we can have these diastereomers there. Or it can add to the same carbon that the methyl group is on. And so like this, or it could add from the other side and push the methyl group to the back. So we could get that. Okay. We can also have the chlorine add to the next carbon. And again, we can get cis and trans isomers here. So that's a pair of diastereomers. And we can also have it add to the next carbon over. And so in that case, once again, we'll get the pair of diastereomers. The chlorine can add cis or trans to the methyl group. And then we can also have it add to the last carbon, so the other terminal carbon here, so like that. And then the other thing that we need to account for is the chlorine could add to that methyl group itself. So there's our methyl group, and the chlorine could add there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are 11 stereoisomers here, okay? And so to address the other two parts of this problem, assuming that products having different physical properties can be separated by fractional distillation, how many different fractions would be obtained? And so we do have a pair of we do have a pair of enantiomers. So these two products here are enantiomers. There's only the one stereocenter, and the difference between these two products is the configuration at that stereocenter. And so they're going to come in the same fraction. Remember, you can't really separate enantiomers, certainly not by fractional distillation. And so the other 9 products will each be in their own fraction. So that gives us a total of 10 fractions for part B here. So 10 fractions if we were to use fractional distillation. And then part C asks us how many fractions would be optically active. And so that one fraction that has a racemic mixture of the enantiomers, that one will not be optically active. All the other fractions will be. So that's going to be 9 fractions that are optically active. So 9 fractions optically active. Okay, again, for this problem, we get these 11 stereoisomers. 2 of them are a pair of enantiomers, and so they will come in the same fraction. So we'll have 10 fractions, and 9 of those fractions, excluding the one that's a pair of enantiomers, the other 9 will be optically active. And that's the answer to chapter 15, problem number 53.